Welcome back to this short series on the fundamentals of control engineering. In the previous video, we have discussed the properties of the Laplace transform, and we have also seen that for the case of stable systems, we can restrict the Laplace transform to the imaginary axis to obtain the Fourier transform of the system. We will explore this analogy further, and we will discuss some interesting properties of the Fourier transform of a linear time invariant system. Let us consider the case where a linear system has in input a sinusoidal signal. As we have seen, the Laplace transform of such a signal is given by the amplitude u times omega over s squared plus omega squared. And we can compute the Laplace transform of the output of the system by multiplying the transfer function p of s times the Laplace transform of the input. Now again, recall that the Laplace transform of the system, P of s, is given by the product of C times S, the complex variable, multiplied times the identity matrix minus A all to the minus 1 times B. And for now, for simplicity, we assume that D equals 0. And this is the product of C times the matrix of the cofactors of S times the identity minus A, all transpose, over the determinant of S times I, the identity minus A, which is a polynomial, and it's the characteristic polynomial of the matrix A, times B. And this is a rational function of the S variable. So for all linear systems, the Laplace transform is a rational function, meaning that it's the ratio of polynomials of S, or possibly of matrices of polynomials at the numerator if you have more inputs or more outputs. And we can write this for a single input, single output system. And a single input, single output system is a system for which we only have one output and one input with n state variables. We can write this as follows. Now let us assume that P of s only has stable real modes, which means that the system will have natural modes that are associated to decaying exponentials. And we can write y of s in the following form. So we have a sum of terms in the form pi over s plus lambda I. Pi are the so-called residuals associated to the lambda I eigenvalues. Plus we have two more residuals which are associated to the terms 1 over s minus I omega and 1 over s plus I omega, which come from the sinusoid in the input. And these residuals q and q star will be complex conjugates because their responses must have imaginary parts that even out and only leave a real response in terms of the time trace of the output of the system. And the residues pi, q, and q star can be computed according to the residue theorem. So q, for example, is the residue of y of s in the pole s equals I omega. So we compute it as the product s minus I omega, so s minus the pole, times y of s, evaluated in s equals I omega. And this is actually a limit for s that tends to I omega. And if we carry out this calculation, what we obtain is p of I omega times the input evaluated in s equals I omega, which is u0 omega over 2 I omega. And simplifying, we have minus I times p of I omega times u0 over 2. And actually, this is an omega naught everywhere, because we are specializing this at the specific frequency of the sinusoid in input to the system. Now we can write the full expression for y of s. So we have q over s minus omega, I omega naught plus q star over s plus I omega naught plus the exponential terms. And we divide this as a y1 and y2. Now for y2, we can take the inverse Laplace transform. Remember that the Laplace transform is linear, so the transform of y1 plus y2 is the sum of the Laplace transform. So for the term y2, we immediately find that applying the properties of the Laplace transform, we can inverse transform the sum in y of s. And let's take a look at what happens when t goes to infinity. So for this term, we immediately see that as t goes to infinity, the exponentials decay. Remember, we assume that our system is stable, so all the lambdas here are positive. And so the term y2 just decays to 0 as t goes to infinity. But for y1, we have to compute the inverse transform of y1 of s. And y1 of s is given by, so we have p evaluated in I omega naught, so p is the transfer function of the plant, times the amplitude of the input over 2i times s minus I omega naught, plus the complex conjugate term p star of I omega naught, again times u over minus 2i this time, times s plus I omega naught. And we can write this as we can now inverse transform these terms. So let's write this through the frequency shift property as p evaluated in I omega naught times e to the I omega naught t minus the complex conjugate coefficient p star times e to the minus I omega naught t. Now we can make use of Euler's formula to decompose the complex exponentials into cosines and sines. Now, if we also decompose p into its real and imaginary part, we can eliminate some of the terms, and we are left with the following. We have the imaginary part of p evaluated in omega naught times the cosine of omega naught times t, plus the real part of p in I omega naught times the sine of omega naught times t. Now remember that the imaginary part of a complex number is given by its magnitude multiplied times the sine of its phase, while its real part is given by the magnitude times the cosine of the phase. And now we can use trigonometric formulas to combine the sine of the phase of p times the cosine of omega naught t plus the cosine of the phase of p times the sine of omega naught t. And the final result we have is the following. The output of our system, when the input is a pure sinusoid, is another sinusoid at frequency omega naught, but with phase given by the phase of the Fourier transform of the system in omega naught, and with amplitude which is scaled by the magnitude of the Fourier transform in I omega naught. Now this result goes under the name of the fundamental theorem of the frequency response. This holds for stable LTI systems and states that if we feed a sinusoidal input to the system, after any transient, the output will be a sinusoid itself, and we call it sinusoidal regime, with the same frequency omega naught, but a phase shifted by the phase of the frequency response of the system, and a magnitude which is amplified by the amplitude of the frequency response of the system. This property allows us to identify experimentally the Fourier transform of the system, which is sometimes also called the harmonic response or frequency response, as we've seen, of the system, by applying sinusoids to it and measuring the outputs. Finally, we have many useful representations of the frequency response of an LTI system. So the frequency response is a complex function of a real variable. So we started from the Laplace transform, which was a complex function of a complex variable. So we had two variables in input, the real and imaginary part of S, and two scalar variables in output, the real and imaginary part of the Laplace transform. Then we scaled it down to the function of a real variable, because now we are just moving along the imaginary axis. So we can look at the frequency omega as a real variable, and we take the function evaluating the Laplace transform in I, the imaginary unit, times omega. And the output is a complex function. So we need to represent it in ways that are not just the conventional representation of a real function. And we have different ways to do so. The first is representing separately the magnitude and phase of the Fourier transform, or of the harmonic response function. And this is called the body diagram. So in the body diagram, we represent separately the magnitude and the phase of P over the frequency. And typically this is done in a logarithmic scale for the magnitude. So we represent the modulus in dB and the frequency in a logarithmic scale, while it's done in degrees versus a logarithmic scale for the phase. As an alternative, we can represent on the same graph the real and imaginary part of the harmonic response function. And this is the so-called Nyquist diagram. This diagram will be very important when dealing with the stability of linear systems. And finally, a third representation, which we won't discuss in this short series, is when the magnitude and phase are represented on the same diagram. So not separately as a function of frequency, but on the same diagram as a curve, which has every point labeled with a different value of omega. And this is called the Nichols chart. We will look at these diagrams more in detail in the next videos.